All right, so for section 10.4, we're going to continue. This is part B, polar coordinates and graphs. So we're going to sketch r equals to 2 cosine 3 theta. So the first thing you're going to want to do is rewrite your x and y coordinate values. So since x and y are r cosine and r sine theta respectively, just plug in your r value that you have, r equals 2 cosine 3 theta, into the x and the y functions, and you can get what they are in parametric form. So once we have that, we're going to plug in the values that I gave you guys. I already prepared these values for us, so pre-calculated them. So what we're going to do right now is just graph this and look to see what the graph is supposed to look like. So let's go ahead and graph this function. Whoops, that's not what I was supposed to do. I was trying to push this graph up here. And then right now I'll show you on Desmos and kind of make a couple of observations with Desmos. But we'll go like 1, 2, 3. So just kind of making a little bit bigger than what we're used to seeing there. So we're starting at 2, 0. So that would be right here. Okay, and then we're going to go to 0, 0. Okay, so we're going to go to 0, 0 after that. Now notice, you may not know, I'm pretty sure you probably don't, but eventually you might, that this graph actually goes like this. Okay, so the question is, well, how am I supposed to know that that's what the graph does? Well, you calculate something in between 0 and pi over 6. So you might want to get that 15 degree, right? So you're going to want to try to get that 15 degree angle to figure out what's missing, all right? So, and right now we can do that at the end. Now, let's continue putting in these values that we're doing here. So at -1, we're going to be at radical 3, so that's 1.71, right? So right about here. Go ahead. Oh, I'm sorry. I think it's supposed to be negative radical. It's supposed to be negative. I'm sorry. Yeah, it's supposed to be negative. Thank you. So it's right here. And what I'm going to do is continue to wrap this around. Okay. And then notice it goes back to 0, 0. Okay, so 0, 0 at this little point right here. So there's the first full petal that you can see. And then we go -1 radical 3. So -1, 1.7. So what it's going to do is it's going to start to go back up here. All right, and notice the next one is -1, 1. So it's right here. So I'm going to kind of go back. All right. And then 0, 0, we already have that. And then 2, 0 is the next point, which I already have. So again, I don't know what's happening right about here. So you might want to get an angle in between 5 pi over 6 and pi, right, to calculate. So every once in a while, when you can't tell what's occurring, it's good to calculate in between angles. But I already do know what this graph is supposed to look like. So it's supposed to look like that, kind of like a propeller. Okay. Now, I'll show it to you guys on Desmos. So let me show it to you guys on Desmos. And it's this graph right here. So notice it does extend. Or hold on, what did I put right here? 2 cosine 3 theta. I think I rotated it, but it's supposed to look like this. I want you guys to notice that the maximum value, I think this thing isn't rotated properly. Yeah, it's supposed to be the way I have it. This way, like that. Yeah, I didn't do it with radians, which Desmos doesn't allow me to do it like that. So I think that might be why it's a little off. But yeah, just showing it like round wise. Yeah. So But the idea is this. Remember, with Desmos, you're supposed to have all of these like circles, right? So here's one of them. Here's another one, right? So you now, of course, my circles aren't perfect, but it's supposed to extend as far out as a radius of 2, okay? And anything in between. These things are supposed to look like flower petals. Just so you guys know, and right now I'll show it to you guys. So check this out on Desmos. If I go up here to where the 3 theta is, and let me notice, if it's a 1 theta, then it's 1 petal, I guess you could say. Okay, if I change it to a 2, it creates 4 petals. So if the number was 1, it created 1 petal. If it's a 2, it creates 4 petals, right? You guys already saw 3. Okay, so 3 was 3 petals. And if I change it to 4, yeah, we have 8. So what's important about that n value in front of the theta? Like, if it's an odd number, how many petals do we get? The same or double? The same. If it's an even number, it doubles, right? If you want to see something kind of crazy, this is kind of interesting. Oh no! But just check this out though. There. So it's actually changing from positive and negative numbers and drawing them in different forms. So yeah, so it's going from negative 10 to positive 10. From negative 10 to positive 10. Yeah, so here's 10. Right. So yeah, if you do like a 20, like you guys said, it would look like that. And the bigger the number, the more of a blob it just becomes, right? So if we do like 200, let's say. Well, there you go. That's 200 petals. Yeah. So, yeah, it's all right. So we'll leave it at this. Okay. So we'll get rid of that, and we'll get back to it. So, definition really quick. Okay, so let's do a definition. So this is theorem 911, but we won't title it. We'll just put slope and tangent lines. And this is what we're going to kind of focus on for the next 2 examples. So let r equal to f of theta. So x equal to r cosine theta and y equal to r sine theta become x equal to f of theta cosine theta and y equal to f of theta sine theta. Okay, no big deal. So using the derivative idea of parametric equations, the derivative for this becomes dy d theta over dx d theta, which looks like this: f of theta sine of theta plus f of theta cosine theta divided by, they're giving you the shortcut. They're not going to make you work it out, okay? And then it's going to be f of theta cosine theta minus f of theta sine theta. I'm not sure if I think there might be another group coming in. Yes. So that's a definition. Now, more importantly than anything, okay, the most important thing that you guys want to take out from this is the following. So I'm going to kind of put a big old thing here. if dy d theta is equal to 0, we have a horizontal tangent line. Okay, so horizontal tangent line. So let's kind of highlight this because this is important for you guys to be aware of. Okay, if dx d theta is equal to 0, we have a vertical tangent line. So let me highlight that there. All right, and the last thing that's super important for these things here, if dy d theta is equal to dx d theta, which is equal to 0. So if both of them give you 0, then we cannot conclude anything from this. Like, we don't know if it's vertical or horizontal, so we cannot conclude anything about the line. All right, so really important that you guys remember that. So again, dy d theta equals 0, dx d theta equals 0, dy d theta dx d theta both equaling 0 have different situations tied into it. Okay, so cannot conclude anything. So the next examples we're going to be doing, they're going to be asking you to find horizontal tangent lines, vertical tangent lines, stuff like that for these polar equations. All right, so let's write down the problem and then see if there's any questions over here. So let's see. This is example number 5. Find a horizontal and vertical tangents lines of r equal to sine theta from 0 to pi. All right, so go ahead and write that down, and we'll get started in a bit. All right, so first off, let's go ahead and make these things into parametrics, okay? So we have x equal to r cosine theta, and we have y equal to r sine theta, okay? Well, that means that x is equal to sine theta cosine theta, and y is equal to sine squared theta. Okay? So if I take a derivative, notice I'm not going to take the derivative that I gave you up here, okay, this big old nasty looking derivative. Like, I'm not going to do that. All they want to know is they want us to find horizontal and vertical tangent lines. Okay, so all I'm going to do is find dx d theta and dy d theta. So let's start off with dx d theta. So the derivative of sine theta cosine theta, that's a product rule. Okay, so the derivative of sine of theta is cosine theta times cosine theta plus sine theta times negative sine theta. That's the derivative of cosine theta. So this is cosine squared theta minus sine squared theta. Now, hopefully you guys remember your trig identities and you say, oh, I know that. That's cosine of 2 theta. So that's going to make your life a lot easier if you can remember your definitions. Now we're going to set this equal to 0. Okay, so cosine of 2 theta equals 0. Okay, So I set it equal to 0 so that I can find out where it has horizontal tangent lines, vertical tangent lines, that whole thing, right? So dx d theta equals 0 will give me vertical tangent lines. All right, that's the definition that I wrote up here. Okay, so dx d theta, that's this one right here. We have vertical tangent lines for that. So let's solve for this. Cosine of 2 theta equal to 0. Well, cosine of an angle equals to 0 when that angle is 90 degrees, right? Or 270 degrees. All right, so what I'm going to say is 2 theta has to be pi over 2, okay? Or 2 theta has to be 3 pi over 2. So that means that theta is equal to 45 degrees or 100 and, what was it, 135? Or we could say 3 pi over 4, right? We'll keep it like that. But that's where it's going to happen, okay? That's my angle when it's going to happen. All right, now just so you guys know, if I show you a picture of this thing, we're talking that function right there. Okay, so that means that at 45 degrees, I'm kind of surprised. I thought it would let me like poke this thing, but I guess it won't. But at 45 degrees, so can you guys see it right there? Let me zoom in. You guys, I'm supposed to be able to click on it, but it's not letting me do it. I'm not sure, maybe because if I'm on a tablet, who knows? If I put, well, you know what? Let me put this keyboard on it, and that'll let me do it. It's supposed to let me do it. Why isn't it letting me do it? Oh, well. Here, I'm going to put the arrow right at it. There's 45 degrees. Doesn't that look like that's the very far right? I don't want to say edge because it doesn't have an edge, but the far right edge to it. So if you were to draw a vertical, a line at that point, it would be, tangent line would be straight up and down, correct? And the 3 pi over 4 is actually over here on this side. Okay? So if you were to put a point right there and draw a tangent line, it would be straight up and down. So would you agree with me that those are the correct angles for vertical tangent lines? Right? Now, I got to find the horizontal tangent lines. That's going to happen way up here and way down here. Right? So let's go ahead and get back to it. So I already found the two angles where that's going to happen. Let's find the horizontal one. So dy d theta. Now, dy d theta, our y value was sine squared theta. Okay? So the derivative of sine squared theta is 2 sine theta cosine theta, which, hopefully you remember, is sine of 2 theta. That's a double angle. Double angles are very, very common on AP stuff. Okay, so make sure you guys know those. So I'm going to set my double angle equal to 0 and ask myself, well, when does this happen? When is sine of what equal to 0? Well, it happens at 0 and pi. Yeah. So I'm going to say sine of 2 theta. 2 theta equals to 0 and 2 theta equals to pi. So that's going to happen at 0 and at pi over 2. And we just saw that, right? It's going to happen at pi over 2. I pointed at it, right? It was all the way at the top and then all the way at the bottom, 0 degrees. Okay? So the last thing you have to do, notice none of these answers, so let me highlight them here for us. None of the angles repeated. You notice that? So that's a good thing. But if an angle repeats, then you can't use it because it can't be a vertical and a horizontal tangent line. Okay, it can only be one or the other. So if it happens more than once, then it's one of those extraneous solutions that, okay, I found it and I solved for it, but it doesn't make sense. Okay, but these are all different. So a lot of times what they're going to want you to do is to list them. So let me list them for you guys. The horizontal tangent lines occur at, so horizontals occurred at the angle of pi over 4. Actually, wait, I think I wrote that wrong. Horizontal, that's a vertical. Horizontal occurred at 0 and at pi over 2. Okay? Now, you got to figure out the R value. So how do I figure out the R value? Yeah, plug it into your sine theta function, right? It was R equals sine theta. So let's figure out R. So sine of 0 is 0. Sine of pi over 2 is 1. So there you go. Horizontal tangent lines. And then our vertical tangent lines. Well, those occur at, it was pi over 4 and 3 pi over 4. Okay? Now, in order to figure out those values, I plug them into sine theta. So sine of pi over 4 would be radical 2 over 2. And the value at 3 pi over 4, that's quadrant 2, would also be radical 2 over 2. That'd be positive. Okay? Now, I know these look like points. Okay? I know these look like points, but they're actually lines, right? They have a length of rad 2 over 2 and an angle of pi over 4, right? So these are actual lines within that. So that's where it occurs. Any questions on that one? I mean, they're not too hard to do, right? Just take a derivative and find the angle. Take a derivative, find the angles. Now we're going to do one more of these just to show you one where like things don't go well, okay? Where you get like a repetition of something. So, and then also like, what if it gets a little bit more complicated? So we just did this one. We're going to do this. I think that's supposed to be a 1. Yeah. Let me change that. That's supposed to be a 1. So we're going to do this one. This one's called a cardioid. Okay? How many vertical tangent lines is it supposed to have? I mean, it's going to have one at the very far left, right? And it's probably going to have 2. One like on the upper right side, where like kind of like the top of the heart and then the bottom of the heart in a sense, right? It's going to have 2 little ones on there. How many horizontals? Yeah, on the very top, right? So on the very top, we're going to have a horizontal tangent line, and at the very bottom of this, we're going to have a horizontal tangent line. So, again, just to kind of give you an idea, I'm just taking a screenshot of this so we can see it. We're going to have a horizontal tangent line probably here and here. And then vertical ones would be here, here, and there. Well, you're supposed to list the points because notice this angle here will be different than this angle there, correct? So it does count, right? This angle will be different, this will be different, but something interesting is going to happen right over here. Because at that point, you actually get both. So that's why you exclude it, okay? Whenever you do that stuff. Hi. So, all right, let's get back to it. Let me write down the example. This will be example 7? 6. Man, I'm off today on my numbering. So example number 7. Oh my gosh, 7, 6. I keep thinking 7. 7's a nice number. So, so example 6 says we're going to find the horizontal and vertical tangent lines. So find the horizontal and vertical tangent lines of the following functions. So we have r equal to 2 times 1 minus cosine theta. Go ahead and write that down. And we're going to do the same thing we just did, only these are going to get a little bit more complicated. A lot more trig is going to have to be used. We're going to have to use some factoring. So a little more interesting, right? All right, so let's check this out. Let's find our x and y components here. So our parametric equation. So x is equal to r cosine theta. Y is equal to r sine theta based on definition. Since our r value is 2 times 1 minus cosine theta, we're going to plug that in. So x is equal to 2 times 1 minus cosine theta times cosine theta. And y will be 2 times 1 minus cosine theta times sine of theta. Okay, so right now we'll go on with this, but let me just check in really quick. Let me pause this. They'll catch up. So let's keep trying our best to do what we can to solve for this. So I noticed they both have signs there. So 2 sine theta on the outside, cosine theta minus 1 plus cosine theta. So it's 2 sine theta times 2 cosine theta minus 1. Now, at this point, hopefully you feel like, okay, I can do this. All right, hopefully you can. 2 sine theta, 2 cosine theta minus 1 equal to 0. Because I already have it factored out, right? So it's not like really complicated. So we'll take 2 sine theta equal to 0 and 2 cosine theta minus 1 equal to 0. So that means sine theta is 0. So that happens when theta is 0 and, I put the wrong thing here, 0 and pi, right? And then over here, we get cosine theta equals to half. So that occurs at pi over 3 and at 5 pi over 3. Right? Quadrants 1 and 4. So great. I found my answers for this. Right? That's where it's supposed to occur. Let me put a little, actually before I do that, let me just write them out here. So theta is going to be 0, pi over 3, pi, and 5 pi over 3. Just to highlight them so we know these are the ones that we found. Now let's do the same thing with y. So we're going to find dy dx. All right, let me go back over here. I'm going to do this the exact same way that I did the previous problem. I'm going to use a product rule. Okay? So I'm going to take out a 2. Now the derivative of 1 minus cosine theta is going to be sine theta times sine theta, right? Because it's 1 minus cosine theta sine theta for y. And then plus 1 minus cosine theta, and the derivative of sine theta would be cosine theta. So I get sine squared theta plus cosine theta minus cosine squared theta. Now I notice there's a lot more cosine thetas than there are sine theta. So what I'm going to do is I'm going to change sine squared theta into 1 minus cosine squared theta. I'm just going to use some identities here. So 1 minus cosine squared theta plus cosine theta minus cosine squared theta is 2 times 1 plus, give me a second, minus 2 cosine squared theta. Okay? At this point, you guys would factor and solve. Now I'm going to do this right now while you guys are gone. I know the class went long, but I'm going to pause it. when you guys are gone during break, I'll finish this lesson. Look at the lesson. I'm going to give you guys homework, okay? So finish the lesson. Go to the 30-minute mark, okay? All right, so what we're going to do is factor. So this will be 2 times, and 1 plus cosine theta minus 2 cosine squared theta will factor into 1 minus cosine theta times 1 plus 2 cosine theta. Now, if you set this equal to 0, we just got to set the 1 minus cosine theta equal to 0 and the 1 plus 2 cosine theta equal to 0. So that means that cosine theta equals 1, or cosine theta is equal to negative half. Now the one part's easy because the only time that cosine of theta is equal to 1 is at 0. Okay, not at pi, because at pi it's negative 1. And cosine of theta equals to negative half at 2 different places, 2 pi over 3 and 4 pi over 3. So our answers are going to happen at 0 and 2 pi over 3 and 4 pi over 3. Now I want you guys to notice something really quick. Hold on, let me highlight this right here. Notice that 0 occurs on the horizontal and the vertical solutions. Okay, so 0 is here and 0 is here. So that means you cannot use 0 because it can't be applied to both. Now, if you remember, I told you there was going to be 3 vertical asymptotes, 3 vertical tangent lines. And notice there's only 3 angles listed. And I told you there was going to be 2 horizontal tangent lines. And notice now there's only 2 listed. Okay, so if they want the actual values where these things happen, then let's see, let's write this out here. So let's start off with pi over 3 pi and 5 pi over 3. So at pi we get 4 comma pi, and pi over 3 we get 1 comma pi over 3, and at 5 pi over 3 we get 1 comma 5 pi over 3. These are the horizontal tangent lines. I'm sorry, vertical tangent lines. Horizontal tangent lines occur at 2 pi over 3 for the angle and 4 pi over 3 for the angle, and that's going to happen at 3 and at 3 here. So here's your solution for that problem. Now your homework is, alright, so homework is page 738, numbers 1 through 6 and 11 through 16.